continuing from the previous video where we looked at a primer for counterfactuals. So I encourage you to check out that video if you have not. But now we are going to take the DAG that we looked at in that previous video right here, okay, and answer a couple of questions about it. Okay, so the first one that we're going to look at is we are meant to find the expected salary of workers who are at Z level or skill level Z equals Z had they received X prime years of college. Okay, and then we're told a hint, which is basically to take this this formula right here and express it as this, and so on and so forth. And we'll get to all of that, but not till later. So so let's start trying to answer this. And so what we're trying to find is the is this expression, right? Again, the expected value of y if we change x to x prime in workers for whom z equals little z. Okay. So rather than attack this analytically, let's use simulation first, and then we'll look at some of the analytical stuff later. Okay, so I'm going to simulate my causal model, right? So I'm going to have a bunch of these data points here. Probably don't need that many. Usually 10,000 is doing okay. Okay, so so I'm just going to recreate the DAG, right? So I have U1, U2, U3, right? U1, U2, U3 isn't shown on the DAG, but I'm adding it. Even if it's not supposed to be there, you kind of need it for the sake of the simulation to make it run without off-putting warnings. Okay, and now notice that x is just a function of U1, z is a function of U2 as well as x, a times x, right? So there's z, ax plus U2 equals z. Okay, and then y is just b times z plus U3. Okay, so we're going to run that. And notice I put a little note here, but I'm rounding my values for z. This is a little bit of this is might raise a couple of eyebrows, but the reason we need to do this for the sake of simulation, I'm not saying that this is just for the sake of the simulation, is because later we're going to select values for which z equals little z, and if z is a continuous variable, well, then there's infinite possible values that it could take on. That's bounded by the precision of a computer. But in theory, there's there's infinite possible values that could be taken on by z, and so none of them will equal little z, whatever I set little z to be equal to. So I'm just rounding them to integers so that we can select data based on z. Okay, that's what's happening there. Okay. So the first thing that we're supposed to do is, according to the book, is to find cases when big Z equals little z. So I'm going to set little z, that's just arbitrary. I'm going to pick a value for little z, I'm calling it z observed. I'm setting it equal to 2. And then to find those individuals for whom z equals 2, I'm finding I'm finding the error terms of the individuals for whom their z value equaled little z. Okay. So I run that. And now in my causal model here, in the next step, in the causal model, wherever there's an x, I'm going to insert x prime and make a new variable here. So, so aside from the definition of x, right? So now I have a new x, it's x prime, and I'm going to arbitrarily set it to 3. Okay. X only shows up one other place. That's here in defining z. So I need to come up with a new z value, z little x, which is just a times x. Now it's a times x prime, and then I'll add back this new error term here in just a second. Okay. In the next step. So so now we need to find a new value for y when x equals x in cases where z equals little z. Okay. Well, what is y? Y is bz times u3. So I have b times my new z, and my new z also has its error term. I hope that's not confusing, right? I just, instead of defining the error term here, I've defined it here. I'm sure I had a reason for it at one point, but I've forgotten it. Okay. And then y also has its own error term, and we're adding back the error term for the cases where z equals z. And so now we're going to so this is going to give us a bunch of possible values, and I want the expected values. So I'm going to take the mean of that big vector and just round it here. Okay, so we get 19.2. Okay, so there's our answer. So just given the arbitrary constraints and values that we put in here, this is the answer. Okay, now it turns out, fortunately, that this answer agrees with the analytical statement that we're given at the beginning, namely that our counterfactual equals the expected value of y given z equals z plus the product of tau times this right here, okay, where tau is the slope of the total effect of x on y from a regression of y on x, right? So tau is just this beta from this separate regression over here. X prime is our x prime value, and then the expected value of x when z equals z. Okay, well we get that from its own regression again. Okay, so now this is the general statement, and in our particular DAG where we have A and B and we could find that this in our particular case equals this. I'm not going to go through it. I don't know if it's really that helpful to do in this case, because I think that the general case is much more interesting. Okay, so so let's make sure that at least in our simulation that this and this agree, or I'm sorry, that this and this with our previous answer agree. Okay, so I'm going to find the expected value of y given z equals little z. So this is just a regression of y on z. A little 0 means there's no intercept, right? Because there's, to correspond with the DAG, there's no intercept here. And then I find the coefficient for z on y. And then to find, the expected value, well, then I multiply the coefficient times z observed. Okay. Tau, again, it's just the coefficient for x in the regression of y on x, right? So I'm regressing y on x, taking the coefficient. Okay, that's tau. And then the expected value of z, or of x given z, well, that's, again, I'm just recreating x after the regression of x on z. So I regress x on z, I take the coefficient of z, and multiply by z observed, and that gives me the expected value of x on z. And then I recreate that expression up there, right? Expected value of y given z plus the product of tau times x prime minus the expected value of x given z. Okay, so let me just run these lines right here just to make sure that we get the right answer, right? So we get 19.2, so that agrees, so that's good. And just for this particular case, again, I'm not going to, but we could break this down and get this expression right here. And so this also should be 19.2, right? And so again, when we run all of this, we get 19.2. Okay. Now the reason that I don't want to focus too much on the specific case, but rather the general case here, is that this is really, really interesting. Okay. Initially, we went through this process of filtering the data to just include particular individuals, and then regressing and then recreating what the outcome would be in those individuals for a particular x value, and da-da-da-da-da. And here we basically just applied the model of a line to our problem and got the same answer. Okay, so it may not look like it, but this is a linear model. This is just the formula of a line, alpha plus beta times x tilde, where alpha is just the expected value of y given z. Tau is the beta term here, right? And in turn, remember that tau is the beta term from a separate regression, y on x. And then x tilde is just x prime minus the expected value of x during, given z equals z. In other words, we are centering, so x tilde is centering x prime around around the expected value of x given z. Okay, so the reason I find this interesting is because every bit of this idea makes perfect sense. Okay, so let's just think about this here. When x prime equals the expected value of x when z equals z, okay, well then this term is 0, which means that this whole term is 0, which means that the expected value of y when x equals x is just the expected value of y when z equals z. In other words, when x prime equals its expected value when z equals z, there's no more information given by x prime that isn't already contained when z isn't, when z equals little z. Okay, so we only need to be concerned with the alpha term here, with the intercept, with the expected value of y when z equals z. But when x prime is not, right, equal to the expected value of x when z equals little z, well then we need to modify this intercept up or down by tau scaled by the extent to which x prime is, different from from the expected value. Okay, so just one more thing before moving on to the next part here. The reason I find this interesting is because I think once you understand what counterfactuals are after, which is really kind of basic once you can wrap your head around it, the two approaches that we used here, I think that you would come up with these by yourself without having to have read it in a textbook. I think that they are reasonably intuitive once you grasp what is being asked here. Okay. Anyway, I don't really have a punctuation point there, but we'll move on to part B. So, based on your solution for A, show that the skill-specific effect of education on salary is independent of skill level. Okay, well, the skill-specific effect is, well, let's just look at it here, okay? It's the expected value of y when x is set to x1 when z equals little z, minus the expected value of y when x equals x naught when z equals z. Okay? When x is set to x naught when z equals little z. Okay, and so we could, so this is the skill-specific effect, right? It is the effect of changing x from x naught to x1 in cases where z equals z, the z-specific effect. Okay, so we could rewrite this as this, okay? And we're meant to show that this equals this, right? Where we could just drop the conditioning on z. Okay. Now, in our basic linear model, this is apparent, right? Because the expected value of y, given, everything, doesn't have z in it, okay? But that seems like a little bit of a cheat because really A is hiding stuff, right? Or alpha, right? Alpha is, where do I have it? Alpha has a z here and x tilde has a, a z there. And so, maybe those are showing up. And so we should go a little bit further. So let's instead expand alpha and beta here, right? So if we take, okay, so if we want to find the causal effect, so we're going to take this guy, okay, and we're going to expand it, right? So we have all of this, okay, where our x prime is x1, and then I'm going to subtract the same thing. Now x prime is x naught, okay, and now notice that if I subtract this term from, or subtract this term from this term, right, that they both have in common this, so that drops out. And so now I'm just left with tau x1 minus tau x naught okay, so I'm going to multiply the taus through, right, so I'll get here and here. Well, now they both have in common this tau expected value of x given z, right? Those drop out. And then I get, so now I'm just left with tau x1, tau x naught, right? Which we could further simplify. But what's important is there's no z in this final expression. Okay? So it's not dependent on z. We could also use the specific case, right, here. Okay, and it's the same thing, right? So we have this expression minus this expression, and we notice that they both have this in common, so that falls out. So now we have abx1 minus abx0, and already, there's no z in here, and so it does not depend on z, and so it's independent of z. Okay, all right, we'll call that good.